Thanks to the organizers for the invitation. It's a real pleasure to be able to speak at this conference to honor Kobe and Sergey, who have done just amazing work individually and of course in partnership. It's like a great cricket partnership. So it really is an honor. I wanted to start by saying that I think, and I confirm this with Kobe, that I might be the person who is known in this room who has known Kobe for the longest time. And in fact, got to meet him when he was just beginning as a graduate student in Berkeley. And I may have had some slight impact on what he does mathematically. And we exchanged letters. This is back in the days when we all wrote letters to each other. And I went to my office, and because I'm a bit of a pack rat, I unearthed some of the letters that Kobe wrote. And so I thought I would start by an extract from a letter Kobe wrote to me in November of 1987. So it starts off, "Dear Charlie, as it usually happens with qualifying exams, it's for you graduate students, it took me a bit longer than I expected to get through with them. But now the exams are over and I'm in search of questions and problems to work on." So then it goes on where he's talking about some of the early O-minimal papers that I had sent to Kobe. But then I think the only other piece I wanted to quote from this before starting the talk is, Kobe asks, "Would you say that there is still work to be done on O-minimality per se?" Actually, it's funny, but it's a good question that Kobe asks, because at that point, some of the results like Alex has proved with showing that you could add exponentiation hadn't been done. And so the examples that have made it such a rich subject hadn't yet been developed. The work of Alex and of course Lau on that stuff. So it's funny, but it was a reasonable question. So I thought I'd amuse us that way. Okay. So let me give an outline of the talk before starting. So first, I want to provide the economics context for what I'll be talking about. Then I'm going to talk about O-minimality and preference and utility theory, which is a really classical topic of study in econometrics. And then I'm going to give a result which classifies O-minimal preferences. And then I just want to ask some questions about what you can refer to as incomplete preferences. And I'll define all the stuff there. So to start, a preference relation is just a binary relation, curly less than, defined on, let's say, a subset of n space that is a preorder, so reflexive, transitive, and complete. And so the way to think about a preference is that you have n different goods, and an individual is making an assessment of which baskets of goods, the different n tuples, the individual prefers. So that's what the preference is expressing. And that's just the classical context for this. And the relation tilde this way, x being less than or equal to y and y being less than or x, is an equivalence relation, what we would call an equivalence relation, what economists call indifference classes. The reason is those n tuples of different quantities of the goods are equally preferred. So there's no, that's why the individual is indifferent with respect to that. It means that x is less than or equal to y, or y is less than or equal to x. So it's a good question actually, because that's really a rationality assumption, you know, in the sense that the person is a completely rational, well, we'll get to that later, but I mean, there are lots of these questions that comes up, but, you know, and makes a judgment about every potential basket of goods. So complete just says you make a judgment about all of them. You don't have incomparable baskets of goods. And a utility function for the preference is a strict order preserving function from the preference relation to the reals. And so what it is really a function on the equivalence classes, on the indifference classes. And this is, you know, basically you can think of it as putting a price, a value on each equivalence class, on each indifference class. And consumer preferences and wants is a classical topic in economics. It goes back certainly to lots of papers by De Breu in the 1950s, who was a Nobel laureate in economics, but it actually dates back to Walras in the 19th century. So this is really a classical topic. And let's see. Is this not working? There. Okay, maybe I just had to turn to it. Okay, and a central question, so, is when does a preference admit a utility function? That is to say, if it admits a utility function, you can put a value on each indifference class of goods, and it's just another way of saying everything can be assigned a price, if you think about it. And classically, economists, so if you go back to De Breu's papers and people around then, would come up with analytic or topological conditions on the preference relation to ensure the existence of a continuous or piecewise continuous utility function. And these analytical conditions are typically continuity-like conditions. So you speak of a preference being continuous, and all that's really saying is, what it really has to do is substitutability of one good for another. So it's saying that you don't have discrete jumps, you know, in preferences. It's really dealing with substitutability. By substitutability, meaning that you can, you know, that goods are commensurable in some sense. That's the language that economists use for this. And so here's where I say a preference is continuous if for each x in P, the sets of tuples that are greater than or equal and less than or equal are closed. And this is what I mean by this substitutability, that as you approach, if you have points that are close, then their limit should be close also. That's what this is saying. What? In the Euclidean topology, yeah. What? Yes. Yes, in P as a subset of Rn. Yeah. Yeah. Yes. That's what yeah, that was in the first slide. That's okay. Other questions at this point?
There's no additive structure. There's no question of, oh, an apple, I want two apples plus an apple.
That's right, there isn't, no. I mean, you know, certainly you could begin to think about that. I haven't encountered that kind of stuff.
Regarding the second part, just that the quotient order is embeddable in R?
Yes, that's right. Order preserving, strict order preserving way. So the question was, is the quotient structure embeddable in R? And that's exactly what it says. Yes. Other questions? Okay. So it took me a while to get comfortable with the topic as well. So as I said, this has to do with so-called substitutability of goods, the fact that goods are commensurable with each other, that, you know, you have unlimited, in these classical models, you have this unlimited substitutability. And there are counterexamples that are well known. For example, just let P be the real numbers and take the preference relation by saying that if, you know, X is less than or equal to Y, if the absolute value of Y, X is less than that of Y, if they're equal, then you prefer the positive one. Okay, this does not have a utility. That's clear because every element in the there are infinitely many pairs that are direct successor or predecessor of each other. So in other words, -3 is the direct predecessor of 3, and that's true for all the real numbers. And so you can't embed this in the reals. Okay, and this can actually be viewed, and this is where we'll get to the context that we'll talk about here. This can be viewed as a so-called lexicographic preference. So how can you do that? You take the positive and negative reals, and you put the positive reals above the negative reals, and so you look at it in R2 as ordered pairs in R2, you know, so the negative reals you look at as 0 or as the number 0 and then 1. So you just look at them one stacked on top of the other. So the direct successor is directly above it. And you can look at this as just a lexicographic ordering. More examples of this are just Rn, where n is bigger than or equal to 2 in the lexicographic ordering. You can't, of course, embed that into R. So these are just examples. But the point is, such preferences, lexicographic preferences, can be used to model consumer choice with a hierarchy of wants and needs. And this stuff goes way back even. So you can see there's a really good paper by Fishburne in 1970 that gives a full discussion of this. So this stuff in the economics literature goes way back. And variants of lexicographic orders, and I'll say more about this in a moment, just try to illustrate with an example, with so-called satiation conditions go back at least to Georgescu-Roegen in 1954, who then credits Menger going back into the 19th century, and there are papers that in the 1970s, 80s, 90s about all of this. So what would be a good example of a lexicographic order arising, a pure one in economics? Suppose you have two goods, or two quantities. You're looking at houses, and on one axis you have the price of the house, and on the other axis you have its proximity to a coal electrical generating plant. There are people who would not pay any price within a certain distance of the coal plant. And so, you know, they just say no way. So in other words, distance would be the first criterion, and then after distance, you rank price. So that's an example of just a pure lexicographic order in this case. But you could also imagine that there would be some blend between the two. So distance from the coal plant would matter, and it would lower the price the closer you are, but there could be a real dependence on it. And those are these kinds of satiation conditions. That's just a way of understanding that. So more recently in environmental economics, and that's why I use the example, I'll just quote from a paper from 2008. So it says continuity in a preference relation is based on the notion of unlimited substitutability between attributes. That is, individuals are assumed to consider and make trade-offs between all the attributes within the choice set. The choice set is the basket of goods, and you make trade-offs, unlimited trade-offs with the different individual goods. And so, however, recent survey evidence, so this is empirical evidence that people have done, suggests that many respondents exhibit signs of having discontinuous preference structures. So one like a lexicographic one that I mentioned, just the toy example there. Discontinuous preferences imply non-compensatory decision-making behavior, such as lexicographic ordering. Such orderings can be classified according to either strict lexicographic preferences, which is what I mentioned, or modified ones where choices based on thresholds and minimal levels of an attribute are necessary. Since results from this study and other valuation studies are used to inform policy decisions, failing to take into account discontinuous preferences could have profound, well, that's a strong word to use, but could have policy repercussions in that the allocation of resources may not reflect the true benefits. So people actually are thinking about the issue of preferences in this way. Okay, so now I'll talk about O-minimality. This leads into O-minimality in preference and utility theory. So there are papers actually going back into the 1990s by Bloom and Zame, and then later by Richter and Wang. These are economics papers. Pursue the issue of when a preference relation definable in an O-minimal expansion of the real field, or even just an O-minimal expansion of a real closed field, that ensures the existence of a definable utility function, which will necessarily satisfy the continuity conditions by O-minimality. And Bloom and Zame actually do a lot more in their paper. They deal with an exchange economy, and I'm not going to say anything about that except to just say that they do this where they actually update results proved in the 1970s using O-minimal in the context of O-minimality to ensure that generically you get finitely many equilibrium prices for an exchange economy, and equilibrium prices where everybody's satisfied, roughly speaking, without going into details. That would take more time than we have. So they do a lot more in that paper. And it was through the Richter-Wang that I first became acquainted with all of this. And so the question is, why restrict to preference relations definable in an O-minimal expansion of the real field? And O-minimal expansions of the field, such as R and X, are, as we know, mathematically rich. And from Bloom and Zame, they say most of the familiar preferences used in applications have such representations. So really the shift is, rather than imposing, purely sort of mathematical hypotheses on a preference and then proving theorems about it, the shift is then saying, let's restrict to looking at preferences definable in an O-minimal expansion and see what we can say there, with the idea being that these are the preferences that any economist who would write down a preference would ever consider. And from Richter and Wang, they say, although we can describe mathematically an agent who maximizes an arbitrary utility function on a budget set determined by an arbitrary endowment vector, I won't describe all these terms, not necessarily, and an arbitrary price vector, the required complexity may exceed what a real-world agent could conceive of or accomplish. Realism may require a simpler framework. So that's what they're talking about here. And I think that this is a convincing argument. So O-minimality also, so when you do econometrics, they use a lot of sophisticated analytical tools in it, topological analytical tools. And the point is, O-minimality provides definably the differential geometric and topological tools that you'll find that economists use. So it's really a good framework in that way in which to work. All right. So now, whoops. Come on, there. So now I'm going to talk about preferences definable in an O-minimal expansion of the real field, and this works. And I have contributions from several people on this, and this is a paper that now I'm finally feeling comfortable enough to put fingers to keyboard, not pen to paper anymore. So I first looked at the Richter-Wang paper seriously, with Breyer and Christian Michaud, and then Alf and Janak Ramakrishnan provide a framework that'll give us the results that I'll talk about. my first contact, Richter started, he actually called me, this back in the days when people would call each other to talk about, it's, pre-Zoom and everything, ask questions about O-minimality for the paper, and it wasn't clear to me then. He wasn't telling me what he was doing, he only sort of asked for stuff. And I confess, I didn't look at the paper until significantly later. And so what they do, so our approach in this paper is somewhat, our approach is somewhat different from theirs. So theirs, they're trying to find a utility, and they really do the kind of classical thing in an O-minimal context. But our approach is different, and we can give a complete analysis and description of preferences definable and expansion of the reals or a real closed field. And it gives a unified picture that I think pulls together the several economics considerations that I've been talking about. How am I doing for time? See, okay, we're doing okay. So I'm going to sort of run through how this works, because it's not difficult up to a certain point where how this works. So the first is the fact that you have definable choice, which is saying that if you have a family of sets in subsets of Mn indexed by a set in Mk, then there is, if you have an O-minimal expansion of an ordered group, a definable function from the parameters to Mn, so that f of a is in the 8th set, and if x of a and x of b are equal, then the choice function gives the same value. So what do I do here? I'm thinking about the set being the indifference classes for the preference, and we're going to apply definable choice to obtain the choice function from P to P. And let L be the set of representatives. So far we're sticking in definability here. And then the point is now, L with the restriction of less than is a linear order definable in M. It's just purely a linear order. You don't have any elements that are equivalent to each other. You're just taking a representative from each class. So then we want to look at this, and then for simplicity, the next two results that I'm going to work in an O-minimal expansion of the order field in M. And so the first thing was a result of Alphonsus and mine, that if you let L be a linear order definable in an O-minimal expansion, let's say of an ordered field, with the dimension of L equal to N, then you could partition, that P should be an L. Okay, well, I mean, what would a talk be if I didn't have at least one typo? Into finitely many sets, x1 through xk, and definable embeddings into Mn with Mn ordered lexicographically. So the point is, you can take a linear ordering, decompose it into finitely many sets, such that on each set, the order you get is actually lexicographic. It might not be, it can be lexicographic in the sense of, if you have a family of curves, you can just think of, the first bit in lex is to march up the family of curves, and then you go within each curve. But that's just the same as a lex ordering. It's just twisted. And then Yannock extended this in 2013. So if you take a linear order definable in N with the dimension of L equal to M, then there's actually he basically saw how you can put all these together into a single embedding, L into M to the M plus 1, with M to the M plus 1 ordered lexicographically, and such that the projection onto the last coordinate is finite. So I'll note this result is optimal. Why is it optimal? I gave you the example before of R ordered lexicographically, where in order to put the ordering on it, you had to add a coordinate. But in the last coordinate, it's finite. You just had a 0 or a 1 in this case. And that's how you ordered that. So this result is optimal. And what it's really saying is the linear order is definable in any O-minimal expansion, let's say, of an ordered field. Are definably lexicographic orderings and, really well behaved. I mean, all you need is just, one more coordinate. Okay?
So you also say that it's just embedding between the M line.
Yeah, you could. Yes, exactly. Yeah, either way. But the whole point is it's just living definably in the original structure. So what's the consequence? Let's then return to the whole idea of preferences. So we're back with remember our set of representatives, and you have the order preserving embedding that you're given by the theorem. And then what this tells us, and again, you can assume by general O-minimality facts that for any k, you can assume that G is CK off a set of small dimension. That's fine, so you get nice smoothness conditions there. A fact is in O-minimal structures, dimension is preserved under definable injections. Thus, if M is bigger than or equal to 2, working in an O-minimal expansion of R bar or an O-minimal expansion of a real closed field, it follows that P does not admit a utility function. Okay, because it's a lexicographic ordering in a dimension higher than 1. Okay, so what we get here is if you take U from P into MM plus 1 by U defined by, if you take in your preference, you take an element X, you first go to its representative in L, and then you compose with G, and you put U of X to be equal to the M plus 1 tuple that you get a definable lexicographic utility. So it's a utility where, of the kind that I was talking about before in the environmental sense, where you have these goods and you have a hierarchy of goods there. What? G is the embedding from the set of representatives into M to the M plus 1. Okay. So what if M is equal to 1? That's the only question really left here. Well, we've seen by an example that P can fail to have a classical utility function, so an embedding into R, if there are infinitely many points X in L that have immediate successors. So just go back to the example that I talked about, and that's the whole deal there. So, okay, good. And we note to all other speakers, you have to turn toward the computer, otherwise this doesn't necessarily function. What?
The last thing was effect on the or on one of them.
See the next slide. Okay, so I'm going to skip this slide because we don't really need it, but I'll go back. I guess I should have said, this didn't appear. But, oh no, it does appear. Okay, so I'll do this and then I'm going to go back and illustrate with a model. I guess I had the wrong order here. No, this is fine. This is where I want it to be. Yeah. Okay. Yeah, somehow I skipped over it. It went too fast. Okay, so here's the answer then, Christoph. So if P is a preference definable in an O-minimal expansion of R bar and L is as above with the dimension of L equal to M, then it's a definably lexicographic preference with vector value utility. That's what I illustrated before. If M is equal to 2 or bigger, and if M is equal to 1, then it has a classical definable utility function if and only if the number of points in the set is finite, the number of points with an immediate successor or predecessor. So what's the upshot of all of this? The upshot is that in the context of O-minimality, all preferences are lexicographic. So it's not just that you have examples of, that lexicographic preferences were an example that classical economists said, look, it doesn't have a utility function, but in fact, this is the entire situation. So it's a complete characterization of what preferences look like in this case. And it really ties together the various threads that I've been talking about. So, all right. And this is the slide I'll skip because I want to spend a little time actually doing a model that I pulled off of, and I'm going to go over to here, a model that I pulled, whoops, oh, okay. All right. I'm in focus. Yeah, what? Ah, okay, got it, okay. So I will want to go back to the project. Can you?
Do you want it now while you're writing?
Yeah, sure. If you can do that, that's fine. So this is where I found the actual model, showing that I'm not sort of just inventing this. And really what it was exactly the kind of situation that I was talking about. So you're going to have two goods. You're going to have, and I'll draw an axis here. You're going to have two goods. One is a sustenance good, G sub S, and the other is an environmental good, G sub E. And you have a preference, which is lexicographic in this case, U bar, which has the two components. It's going to have U sub S. So the priority is sustenance over environment. That's the basic one that you have. So you have U sub S being a function of G sub S, G E, and then U sub E, G sub S, G sub E. So this is an example of a situation where you're going to get a vector valued utility here, okay, vector valued utility. And each of these is, if you give priority to sustenance, it depends on both the goods, what your need for the sustainability good and your want for the environmental good. And the thing is that these two can interact. I mean, the example that he mentions is, that if you're making furniture from sustainably sourced wood, you're actually doing an environmental good, but it's also a sustainability. So it's where you don't have a pure, absolute environmental good or sustainability good ruling. So, okay. And then you have satiation conditions. So the satiation conditions say that you've satisfied the sustainability good. Okay. And it looks like a curve like this. I'll call this U sub S star. So what this says is along here, you've satisfied the sustainability demands. And it shows an interaction between the two, but the reason why it's curved this way is you value sustainability in this sub-utility. you value sustainability above the environmental concern. And so you're going to have indifference curves for use of S that look like this. I actually had to practice it because otherwise I would have screwed it up massively. It was confusing enough as it is with being. So then similarly, you have a satiation condition for the environmental component here. Yes, yes, but the point is, this is a maximum. This is telling you when you've satisfied the condition. So anything above this would say you've satisfied those conditions. What? That this combination of goods is maximal from the sustainability point, that any combination here is fine for this sub-utility here that gives priority to the sustainability good. And similarly, you have curves for U sub E. So this is going to be U E star. And this is to reflect the fact, the reason why the curve looks like this is to reflect the fact that you're giving priority to the environmental good. And then you have indifference curves that look like this. So really then, what's going on is you can look at different regions. So you can look at this region here, like that, where you've already satisfied the environmental good, but the point is that it's all you care about is where you live here. Similarly, if you look at this region here, this really does have a classical utility because all you care about is maximizing in a point in here. You don't care anymore about the sustainability good, you just care about maximizing the environmental good. But then in this region here, this is a true lexicographic preference because if you take 2 points in here, you first look to see which has a higher U sub S, and then you look to see which has a higher U sub E. And this is the kind of thing that can happen, and this is the kind of thing that happens in the O-minimal context, but it's all that can happen, is the point. There's nothing else going on. I survived that. And I didn't create this example, and that's why I'm saying people really do think about these things. And so, all right, how am I doing on time? I have 10 minutes? Okay, good. That's fine. What? 12 minutes? Okay, that's fine. Perfect. Okay, so then what I want to turn to is this gives this complete picture of what's going on in terms of preference theory in O-minimality. And the interesting thing, as I said, is that it takes the classical bit and also what was perceived as just examples and what later turns out to be something that when people do surveys and look at people's actual attitudes, they see things functioning lexicographically within limits. It says this is all that happens for these preferences. This is the whole story. So it's not just examples, it's the whole picture. It really does look like that. But I want to talk a little bit about incomplete preferences. So an incomplete preference, what do I mean by this? This is where you can have incomparable elements in it. And so this is taken from a paper by an economist at New York University, F.A. Oak, and I've extracted this. It is of interest to model the behavior of boundedly rational individuals in economics, and as discussed thoroughly by these 2 older papers, among others, there seems to be no a priori reason why a rational decision maker cannot exhibit indecisiveness, and that's not indifference. So indecisiveness is saying I'm looking at these 2 and I don't care. I can't compare them. Sorry, it's not that I don't care, it's that I can't compare them. you know, in certain choice problems. And daily practice would provide many instances to this effect. And apart from their realistic appeal, there's another reason why incomplete preferences provide a conservative modeling technique in those situations in which the modeler only has partial information about the preferences of an agent. So this is something that this economist is looking at. And so then this leads to questions I have. I don't have answers, but questions, and I'll raise those. I thought that would be a nice place to end the talk. Oops, gotta go this way. So question is then, what can be said about partial orders definable in an O-minimal expansion of a real closed field? I mean, we know what linear orders look like. We have a perfect description of them. What about partial orders? Well, one thing when you're thinking about partial orders is the width of a partial is, excuse me, well, that is true too, but it's the dimension of a partial order. So if you take a partial order, it can be written as an intersection of linear orders that extend it. Okay, this is classical, and you can say that a partial order has finite dimension if there are a set of finitely many linear orders that give the partial order as their intersection. And for a while, I hope that, well, okay, let me just then state a result in this direction. It's a result of Janak's and mine for about 5-6 years ago. And it says, suppose you take a partial order definable even in a weakly O-minimal structure, M, then it can be extended definably to a linear order. So the upshot of this is, if you're thinking about extensions, is that you have a very nice understanding of what this linear order looks like. It's a lexicographic order. And so, you know, naive hopes have spurred lots of mathematics. And even though it's incorrect, I said, well, wouldn't it be great if partial orders all in O-minimal structure all had finite dimension, and that finite dimension could be realized definably? Then you really get a lot of information about what these partial orders look like and what incomplete preferences would look like. It would give you tons of information. It would be almost classical in the sense of more or less looking at partial orders where on n-tuples, where the relation of one n-tuple being bigger than the other is that if it's bigger than or equal in each coordinate. It's called the Pareto order, classically. So I thought, oh, that would be great, but that's false. That hope was quickly dashed. But then the question becomes, what if you then say, so here's, and this comes from Oak too, because he considers these issues, is suppose you say that somebody is indecisive, yeah, but not that often. So what does that mean? One way of saying that is that the size of a maximal antichain is finite. That is to say, the partial order has finite width. Okay, again, another topic. And in that case, finite width partial orders can be written by Dilworth's theorem as a union of finitely many chains or linear orders. And then in that case, once you're there, you know that that implies finite dimension of the partial order. That's easy to see. Sorry, okay. What? I think I told you, but that's okay. Maybe I didn't, okay? Jet lag, whatever you want to call it. So what it says is that every partial order can be written as an intersection of linear orders extending it if there's a finite number of them. The smallest number is the dimension. Well, yeah, right, okay. Yeah, I think I know that, yeah. So, right. So in this case, what I was thinking about is, can you give a nice description even of finite width partial orders definable in an O-minimal structure? So for example, could you get a definable version of Dilworth's theorem, which in turn would then allow you to get the set of linear orders that you need in order to realize the partial order definably. Everything then becomes definable, and once things become definable, we know what the linear orders look like. So I just want to close with putting that question out there. And I haven't written it out because I wasn't sure that I wanted to claim it as a question. It was in fact naive, but rather just to state it. And I think that would be interesting because, again, it would enable people to really understand what even incomplete preferences look like from the economics point of view. So, all right. So, happy belated birthday, Sergey. I did not have a photo of you with one of these silly hats on, but I promise you, if you really want one, I'll get one for you. This is Kobe, and this is the chair of this session. And it turns out that this is now my 30-year-old daughter. So I'll close with that. Thank you.